Welcome to another episode of Automat Devlogs. Today we are going to talk about Automat scripting approach, which is kind of unique. The way we do scripting in Automat is that we are using assembly, but the way we are using assembly for scripting is slightly different because we don't want only expert users who know assembly, who know how to program to use it. We would like to regular person who's just opening Automat for the first time to be able to use assembly to do useful logic as fast as possible. So we're trying to minimize the time to build useful programs. We are aiming for an average person to use assembly, and we want this to be true assembly, not some kind of virtual machine. Our approach, which we mostly implemented already, is to use cards that can be connected together to express relations. Those cards are then converted into machine code when assembly is executed. So here, for example, you can see a macro that does automatic ingredient farming in Skyrim. Okay, but the problem that we were trying to solve recently was to show conditions in a way which would signal to the user what the condition does, that the condition can be changed, and something that would also help the user build a mental model for how the conditions work, when they will be on or when they will not work. The way we approached it is that we are using a flat card metaphor. So to signal the user that something can happen here, we went with this pane of glass that hides a symbol. By just a subtle gradient, you can immediately tell that something can happen here, that it can be pressed, scrolled, something can be done with this object. So this is an interactivity signal. It could probably also change the mouse pointer to a hand, but this is still to do. It will happen. The thing that user usually does when they see something that's distinctive is they either click it, which in our case changes the code to a different one, or to scroll it. Scrolling also works. We also made the scroll work in any direction, so it can be scrolled vertically, horizontally, and it switches between different scroll modes. When you look at this from far away, the most visible element of this button is the black symbol at the center. We are trying to avoid usage of the black color so that it's something that you see first when you look at this. We picked the symbols so that they can be read in the context of the text around. So when you have this, you can just read it aloud as if less than equal, then jump. Similarly for the others. Those three are the conditions that we have. If not equal, then jump. But this is just the bird's eye view of this icon. When you zoom in, you can see that there are more elements here. We have those regions around the border, and we have some gray symbols around it. What they are? They are part of something of a bigger design that's actually not there yet, so I will have to ask you to use your imagination now. We are using a metaphor of dial to represent numbers in computer memory. The goal of this is to teach the users how numbers work inside CPU registers. Specifically, we have two types of operations that use different colors, and they signal the equivalence between signed and unsigned numbers. There is a region of numbers that can be represented in both of them using the same way, but when we switch to negative numbers or very high positive numbers, those operations are kind of distinctive, sometimes, not always. Some operations like the equality checking, find equality, they work for any numbers. We use color purple for them. And when operations work on signed numbers, we use the blue color to show that they use negative part of the dial. Different parts of the dial also signal number of bytes that we need to represent a number. So here we have 8-byte numbers, positive and negative, then 16-byte numbers, 2-byte numbers, 16-bit numbers, then 4-byte numbers, 32-bit numbers, and finally 8-byte numbers or 64-bit numbers. Also, the overflow mechanism, which overflow happens when we are adding numbers and the needle on the dial crosses this position. This is when we use the symbol for overflow. Let me find it. Yeah. We show a crack in this section and also display it as water within the dial. The water, which by the way is simulated. So it's a wavy water, wobbly water. So this is how we are displaying numbers. There are also operations, there are also conditions in x86 that can check for number of bits in the lowest byte of a register. It's very fringe use case, but we're still displaying them using flags. So we can check for even number of flags, or for odd number of flags, or even number of flags. And we can also highlight the receptive region on the dial here. So the reason we are going with this dial is that when we show to the user that numbers can be compared, this comparison, we are going to, although we are doing this using English language right now, eventually we are going to use this using animated image of a scale, where you put a register on one plate of the scale, and on the other plate of the scale you can put either another register or maybe some immediate number like here, or even hexadecimal number or an ASCII, or actually Unicode UTF-8 value. So this is how we represent comparisons in Automat, and how we help with building the mental model, or how the numbers work. And this can immediately be used in our macro, in our Skyrim macro, where we check for equivalence with a piece of text actually here. So we're using register to store a piece of text, and we are comparing the value inside the register with this piece of text here. Okay, this is it. See you next time for more progress. Bye bye.